The loudest sound in a hospital basement isn't the roar of an engine. It's the silence of an 800-kilowatt generator refusing to start while the facility hemorrhages $17,000 an hour. For 47 days, this Cummins VTA28 had sat cold, a 12-ton paperweight anchoring the hospital's anxieties. 3 separate teams of certified technicians had come and gone. They brought laptops, scanners, and invoices totaling $60,000, leaving behind a machine that still refused to synchronize with the grid. The facility manager was ready to sign the scrap order. He didn't understand that the machine wasn't broken. It was just waiting for someone who spoke its language. To understand the scale of the failure, you have to understand the machine. The Cummins VTA28 isn't just an engine. It is a monument to a specific era of industrial might. We are talking about 12 cylinders arranged in a V formation, displacing 28 liters, weighing over 12,000 pounds. It was built in the mid-70s, a time when engineering was defined by cast iron and mechanical linkages, not silicon and software. It sits on its isolation pads like a sleeping giant, indifferent to the panic of the administrators upstairs. And there was panic. Modern hospitals are organisms that run on electricity. When the mains fail, the backup isn't a luxury, it's oxygen. Without this generator, the MRI machines are just expensive magnets, and the operating theaters go dark. But instead of a solution, the room had become a crime scene of incompetence. I walked past the yellow safety lines and saw what I always see in these situations: the graveyard of parts. It was a pile of cardboard boxes stacked haphazardly against the wall, each containing a perfectly functional component that had been ripped out in a desperate attempt to guess the problem. There were electronic control modules, voltage regulators, speed sensors, and actuators. I picked up a voltage regulator from the top of the stack. It was a brand new Basler unit, worth about $800. It had been installed, tested for 5 minutes, and then discarded when the engine didn't immediately correct itself. This is the signature of the modern parts changer. A parts changer is not a mechanic. They are technicians trained to read error codes. When they plug their laptop into a machine and the screen tells them sensor A fault, they replace sensor A. If that doesn't work, they replace the wiring harness. If that doesn't work, they replace the computer itself. They treat the symptoms because they don't understand the anatomy. They view a machine like this VTA28 as a black box. Input fuel, output electricity. They don't understand that between the fuel tank and the transfer switch, there is a complex symphony of fluid dynamics, thermal expansion, and harmonic resonance. They were trying to diagnose a mechanical soul with a digital stethoscope, and the machine was simply ignoring them. The bill on the manager's desk sat at $60,000. For that price, they had purchased nothing but confusion. They had replaced the fuel solenoids because the computer said low pressure. They had replaced the governor control unit because the computer said signal loss. They had even replaced the entire exciter assembly on the back of the alternator. None of it mattered. The machine didn't care about their new electronics because the problem wasn't electronic. It was a fundamental misunderstanding of how a 12-cylinder diesel engine breathes. These shops bill by the hour and mark up parts by 40%. It is a business model built on the assumption that the customer knows less than the technician. In this case, that was true. But it is also a model that collapses the moment it encounters a problem that isn't in the manual. The hospital administrator stood by the door, checking his watch. He looked at the pile of wasted parts and then at the silent engine, calculating the cost of a replacement unit. He saw an obsolete relic that had outlived its usefulness. He didn't see the engineering integrity that lay beneath the layers of dust and neglect. He didn't see that this machine was built to run for 50,000 hours before a major overhaul, provided you treated it with respect. He just saw a liability. I didn't bring a laptop. I didn't bring a diagnostic scanner or a team of assistants. I walked in with a weathered leather satchel that had seen the inside of more engine rooms than most people see in a lifetime. Inside, there were no flashing lights or digital readouts. There was a set of high-quality wrenches, a multimeter, a mechanic stethoscope, and a pair of heavy-duty hearing protection headsets. The manager looked at my bag with skepticism. He was used to technicians who looked like IT support, arriving in clean uniforms with tablets. He wasn't used to someone who looked like they were there to perform surgery. But that's exactly what this was. The machine wasn't dead. It was in cardiac arrest, and the defibrillator everyone else had been using was set to the wrong frequency. I put on my headset, not to block out the noise, but to prepare for the conversation I was about to have with 28 liters of displacement. The generator room was sterile. That was the first thing that offended me. In a hospital, sterility is a virtue. In a mechanical room, it is a deception. The floors had been scrubbed with industrial solvents, leaving the concrete gleaming under the fluorescent banks. The walls were painted a bright, reflective white. It looked less like an engine room and more like a laboratory, a place where dirt was the enemy rather than a byproduct of work. This clinical cleanliness was a mask. It was an attempt to impose order on a chaotic failure, to scrub away the evidence of the machine's refusal to cooperate. But you cannot scrub away the atmosphere. I stopped 3 feet inside the door and just breathed. The facility manager started to speak, offering a handshake and a preamble about the facility's safety protocols, but I walked past him without a word. I wasn't being rude, I was calibrating. To the uninitiated, a generator room smells like diesel and grease. To a specialist, the air is a dense narrative of chemical reactions. I closed my eyes and inhaled deeply through my nose, filtering the background scent of floor wax to find the underlying notes. It was there, faint but unmistakable. The sharp, acrid tang of burnt ozone. That told me the brushes on the exciter had been arcing, likely fighting a voltage irregularity that the regulators couldn't smooth out. Below that, there was a heavier, sweeter smell, sheared oil. Not burnt oil, which smells like carbon, but sheared oil. It smells like hot metal and broken polymer chains. It's the scent of a lubricant that has been squeezed between two metal surfaces at such high pressure that its molecular structure has literally been torn apart. It suggested that the bearings were fighting a load that wasn't purely rotational. The machine had been struggling to turn, physically fighting its own geometry. I opened my eyes and approached the VTA28. Up close, the sheer mass of the engine block was imposing. It was a landscape of cast iron, painted in the classic Cummins beige, now stained with the dark sweat of its recent trials. I ignored the glossy new parts the previous teams had bolted on and looked at the floor near the mounting pads. The cleaners had done a thorough job, but they had missed the corners behind the vibration isolators. I crouched down, shining my penlight into the crevice. The dust there told a story the sensors had missed. Dust settles differently depending on the vibration frequency of the floor. Low-frequency rumbles create piles, like dunes in a desert. High-frequency vibration, the kind caused by harmonic dissonance, makes dust behave like a fluid, spreading it into thin, ripple-like waves. The dust here was rippled. This machine hadn't just been vibrating, it had been shivering. It was a structural resonance, a shudder that started in the crankshaft and radiated out into the concrete. Rising, I moved to the exhaust manifold. I ran my hand hovering an inch above the metal. It was cold now, but the discoloration on the cast iron remained. The manifold on the left bank was a deep, consistent rust color, but the manifold on the right bank, specifically around cylinders 4 and 5, had a slight bluish tint to the oxidation. That meant heat. Excessive, localized heat. The previous technicians had seen an engine that wouldn't sink. I saw an engine that was fighting itself, with half the cylinders working harder than the others to maintain the same RPM. I traced the work of the certified teams. It was a catalog of disrespect. They had installed a new camshaft position sensor, but they had secured the wiring harness with cheap plastic zip ties, pulling the wire tight against the hot water jacket. The insulation was already beginning to soften. They had replaced the fuel rail pressure sensor, but looking closely at the flange bolts, I could see the fresh tool marks were uneven. They hadn't used a torque wrench. They had just cranked it down until it felt tight. On a machine like this, tight enough is a measurement of failure. Uneven torque on a flange warps the mating surface, introducing microscopic air gaps that destroy vacuum pressure. The machine felt offended. That sounds unscientific to people who work in offices, but anyone who has spent a decade in the field knows that machines have temperaments. This VTA28 had been built with tolerances calculated by slide rules and verified by master machinists. It was designed to operate in a state of perfect mechanical equilibrium. The previous teams had treated it like a broken toaster, swapping parts without understanding the system. They had insulted its engineering. I placed my hand flat against the cold valve cover of cylinder number 1. I wasn't praying. I was establishing a baseline. I needed to feel the temperature of the metal, the density of the casting. I was listening to the silence of the room, waiting for the ghost of the vibration I had seen in the dust. "Excuse me," the facility manager's voice cut through the air, sharp and impatient. I didn't turn around immediately. I finished tracing the line of the fuel injection pump with my eyes. I asked where your laptop is. The other teams needed to plug into the diagnostic port immediately to read the fault history. We don't have all day for you to admire the antique. I turned slowly, adjusting the heavy hearing protection around my neck. The manager was holding a clipboard, tapping it rhythmically against his leg. He looked at my weathered satchel, then at my empty hands. He saw a woman without a computer standing in front of a complex digital problem. He saw a scam. I saw a man who was about to learn that physics doesn't care about his schedule. "I didn't authorize this visit to have someone stand here and meditate," the facility manager said, his voice echoing sharply off the tiled walls. He tapped the clipboard in his hand, a nervous, rhythmic tick. "We have a purchase order pending for a Caterpillar C175. It is a $2 million investment, but it comes with a warranty and a service team that actually uses diagnostic software." He gestured vaguely at the VTA28, his hand waving dismissively at the 12 tons of iron. "This thing is a dinosaur. It was installed in 1976. It is obsolete. The previous teams were certified Cummins technicians. They had the latest firmware updates. They scanned the entire system and told me the motherboard is fried. If they couldn't fix it with their equipment, I fail to see how you are going to fix it with a screwdriver and a flashlight." He stepped closer, invading the personal space I had established around the engine. He smelled of hand sanitizer and stress. "To be honest," he continued, his tone hardening, "I think this whole independent specialist thing is a scam. You come in here, charge a premium for consulting, wave your hands over the engine like it's some kind of mystic ritual, and then tell us we need a new one anyway. I am giving you this access strictly because the hospital board insisted on a final opinion before spending the capital. But do not waste my time. Where's your laptop? Where's your connection to the factory server?" I looked at him. I didn't blink. I didn't raise my voice. When you work with 12-liter diesels that generate enough torque to twist a chassis frame, you learn that the loudest thing in the room is usually the one doing the least work. I let his accusation hang in the air for a moment, letting the silence maximize the weight of my response. "The reason those certified teams failed," I said, keeping my voice low and measured, the voice of someone who knows exactly how the machine works, is because they were looking for a software problem in a hardware world. They told you the motherboard is fried because the sensors are sending erratic data. But the sensors aren't lying. They are screaming. I walked over to the pile of discarded parts and picked up the ECM they had replaced. I held it up like a piece of evidence in a courtroom. "This computer is designed to manage fuel timing based on a stable rotation. It assumes the crankshaft is spinning smoothly. It isn't. The engine is fighting a harmonic resonance. The computer sees that vibration as a timing error, so it tries to correct it by adjusting the fuel injection. That just makes the vibration worse. It is a feedback loop. You can replace this computer 1,000 times. You can buy a $2 million C175 and install it right here. But if you don't understand why the physics are failing, you are just changing the serial number on your problem." I set the ECM back down on the stack of wasted money. "You call this a dinosaur," I continued, pointing to the cast iron block. "I call it a machine that was built before planned obsolescence became a business strategy. This engine doesn't need firmware. It needs synchronization. The vibration I saw in the dust isn't a ghost. It is a mechanical dissonance. Something in the hydraulic governing system is fighting the electrical load. Your previous teams replaced the electronics because that is what they sell. They sold you $60,000 of symptoms. I am here to treat the disease. The scam isn't the specialist who listens to the engine. The scam is the shop that bills you for parts they didn't need to install because they were too lazy to read the blueprints." The manager's face reddened. He wasn't used to being lectured by someone in grease-stained coveralls. He looked at his watch, then back at the purchase order on his clipboard. He was cornered by his own budget and the ticking clock of the hospital's vulnerability. "You have exactly 1 hour," he he said, his voice tight. At 11 a.m., I am faxing this order for the replacement unit. If this generator isn't online and holding the hospital load by then, you pack up and leave, and I don't want to see an invoice. It was a bet. He was betting $2 million of the hospital's budget against my ability to hear what a machine was saying. He wanted me to fail. It would validate his decision to scrap the old iron. It would prove that he was right to trust the men with the laptops. I put the hearing protection over my ears, sealing out the hum of the ventilation fans. The world reduced to a muffled thrum. I looked at the manager and spoke loud enough to be heard through the plastic cups. I don't need an hour, I said. I need you to clear the room, and I need you to authorize a startup. I don't need to fix it in an hour. I just need it to run for 5 minutes. If I can't find the fault in 5 minutes of runtime, you can scrap it. He hesitated, surprised by the compression of the timeline. Then he nodded, a smirk playing on his lips. He thought I was bluffing. He reached for the control panel to initiate the start sequence. He didn't know that 5 minutes in a room with a resonant V12 is an eternity. It is plenty of time for a machine to tell you exactly how it is going to die. The manager pressed the start button, and the room instantly ceased to be a sterile laboratory. It became a combat zone. The air start system engaged with a pneumatic shriek, a violent hiss of compressed air slamming into the cylinders that bypassed the need for electrical starter motors. For 2 seconds, there was only the sound of mechanical resistance, the heavy steel crankshaft fighting the friction of cold oil. Then, compression ignited. The VTA28 didn't just turn on, it detonated into existence. A plume of black smoke, the result of a cold fuel rack opening wide, erupted from the exhaust stack before the turbochargers could spool up to clear it. The floor beneath my boots jumped. The sound was a physical weight, a rhythmic, concussive thumping that resonated in the chest cavity. This is the throaty rumble enthusiasts talk about, the specific acoustic signature of a 12-cylinder engine firing in a sequence designed for power, not politeness. But underneath the roar of combustion, I heard the sickness immediately. A healthy generator at idle should sound like a freight train, monotonous, heavy, and absolutely consistent. This engine sounded like it was arguing with itself. It would surge, the pitch rising aggressively as the turbos wind up, and then it would stumble, the RPMs dropping as if it had suddenly run into a wall of molasses. This is called hunting. The engine was searching for a steady 1800 RPM, but it couldn't find it. I stepped closer, placing my hand directly onto the valve cover of the number 3 cylinder. The vibration was jagged. I closed my eyes, letting the hearing protection filter out the high-frequency turbo whine so I could focus on the lower frequencies of the block. I needed to separate the combustion noise, the explosions, from the mechanical narrative. The problem was the interaction between the hospital and the machine. Modern hospitals are full of dirty power. MRI machines, X-ray scanners, and variable frequency drives on HVAC fans are non-linear loads. They don't draw current in a smooth sine wave. They sip it in jagged gulps, sending harmonic distortion back into the grid. A modern digital governor filters this noise out. But this VTA28 had an analog hydraulic governor. It was a mechanical device trying to read a corrupted electrical signal. The flyweights inside the governor were reacting to the harmonic noise as if it were a load change, opening and closing the fuel rack in a panic. The machine was trying to sync with a ghost. The hunting grew worse. The engine surged to 1900 RPM, the roar deafening, then dropped to 1600, the whole frame shuddering on its mounts. The vibration was so intense that the pile of cardboard boxes in the corner toppled over. The manager's eyes went wide. He saw a machine about to shake itself apart. He saw the piston rods threatening to exit the block. He lunged for the emergency stop button, his hand trembling. I moved without thinking. I stepped between him and the panel, my arm shooting out to block his hand. He shouted something at me, his face twisted in fear, but I couldn't hear him, and I didn't care. I needed 30 more seconds. I didn't need to save the engine. I needed to hear the failure mode. I needed the break point. The surging became violent. The turbochargers were gasping, spooling up and down in a chaotic rhythm. And then I heard it. It wasn't a grind. It wasn't a knock. It was a high-pitched, piercing scream that cut through the diesel roar like a scalpel. It lasted for exactly 2 seconds. It was the sound of high-pressure hydraulic fluid being forced through a gap that was too small. It was a scream of shear. Immediately after the scream, the engine choked. The governor collapsed, the fuel rack slammed shut, and the VTA28 died. The silence that rushed back into the room was heavier than the noise had been. The manager stared at me, his chest heaving, convinced I had just destroyed his asset. I pulled off my headset, the ringing in my ears fading. I didn't look at him. I looked at the hydraulic lines feeding the governor. I had heard exactly what the scanners had missed. The room was silent, but it wasn't peaceful. It was the heavy, suffocating silence of a bomb that had just failed to detonate. The manager was pressed against the back wall, his face pale, staring at the VTA28 as if he expected it to explode. He saw a catastrophic failure. I saw a successful stress test. The engine had told me exactly where it hurt, screaming the location of its injury in that final 2-second shriek. Now, the clock was running. I didn't look at the manager. I didn't look at the clock on the wall. I had roughly 17 minutes before the residual heat in the block dissipated and the hydraulic pressure normalized, hiding the evidence. I moved to the side of the engine, stepping over the yellow safety line. The heat radiating from the 12-cylinder block was intense, a physical wall of thermal energy that smelled of curing paint and hot iron. The cooling fans had spun down, leaving the air stagnant and thick. Most technicians would back away, waiting for the machine to cool down to a safe touch temperature. But temperature is data. In the world of hydraulics, heat is the footprint of inefficiency. If energy isn't being converted into motion, it is being converted into heat. I needed to find the hot spot before the iron soaked it up and equalized the temperature gradient. I bypassed the electrical harness entirely. The bundle of wires leading to the ECM was irrelevant. The computer had already confessed its ignorance by shutting the system down. Instead, I focused on the hydraulic lines feeding the Woodward governor. This system uses engine oil pressure to articulate the fuel rack. It is a closed loop of fluid dynamics, purely mechanical, and completely invisible to a digital scanner. I removed my gloves. You can't diagnose a hydraulic fever through leather. I placed my bare left hand on the steel-braided line feeding the inlet of the proportional valve. It was hot, roughly engine oil temperature, maybe 180 degrees. That was normal. Then I moved my hand 6 inches to the right, to the return line exiting the valve. It scorched my skin. I pulled my hand back, wincing, but I had my answer. The return line wasn't just hot, it was scalding, easily 40 degrees hotter than the supply line. That is a massive thermal spike across a 6-inch span of steel. In a hydraulic circuit, a temperature delta like that means one thing: shearing. The fluid was being forced through an orifice that was too small, or it was being churned in a tight space until the friction tore the molecular chains apart. The energy that should have been moving the fuel rack was instead boiling the oil. This was proportional drift. The valve wasn't broken. If it were broken, it would be stuck open or closed, and the temperature would be uniform. Instead, the valve was fighting a hydraulic lock. It was trying to push the spool to the commanded position, but the fluid on the other side had nowhere to go. It was like trying to close a door against a stiff wind. The door vibrates, hovering in the middle, doing a lot of work, but going nowhere. I needed to confirm the internal state of the spool. I reached into my satchel and pulled out my long shank screwdriver. The manager took a step forward, likely thinking I was about to start hitting the machine, but he stopped when he saw me place the metal tip against the valve body and press the plastic handle against the mastoid bone behind my ear. This is the oldest diagnostic. It was a faint, high-pitched hiss, like a tea kettle 3 rooms away. Thump. Thump. The spool was fluttering. It was bypassing fluid internally. The whine I had heard during the shutdown wasn't a bearing failing. It was the sound of oil reaching supersonic speeds as it squeezed past the lands of the spool. The valve was frantically trying to find center, but it couldn't. I pulled the screwdriver away. The diagnosis was complete. The modern shops had replaced the electronics because the signal was erratic. They never realized the signal was erratic because the valve was physically incapable of holding a steady position. But here was the kicker. The valve wasn't worn out. The hiss was too clean, too rhythmic. A worn valve sounds gritty. This sounded like a flow restriction. The valve was fighting a blockage that shouldn't exist. It was behaving as if the return port was capped off. And that's when the realization hit me, cold and hard. This wasn't a failure of age. This was a failure of birth. I turned away from the engine, wiping the grease from my hands onto a rag. The manager was watching me, waiting for the bad news. He expected me to say the engine was dead. He expected me to ask for a new part. "Well?" he demanded, his voice tight with the expectation of victory. "What's the verdict? Wiring harness? Main bearing?" I didn't answer him. I walked over to my satchel and unbuckled the main flap. I didn't reach for a wrench. I didn't reach for a sensor. I reached into the back pocket and pulled out a thick, yellowed envelope that smelled of old libraries and basement storage. "I don't need a part," I said, turning back to him. "I need you to look at history." I cleared a space on the polished concrete floor, sweeping away the invisible dust of the manager's skepticism with the side of my boot. I knelt down and unrolled the documents. They weren't PDFs on a tablet screen, and they weren't printouts from a digital manual. They were large, D-size vellum sheets, printed in the distinct blue line style of the mid-70s. The paper was brittle, cracking slightly at the folds, but the ink was as sharp as the day a draftsman in Columbus, Indiana, laid down the lines with a straight edge and a steady hand. "This," I said, smoothing the curling corners flat against the cold floor, "is the DNA of your machine." The manager looked down, frowning. He saw a maze of lines and symbols that looked like hieroglyphics. He was used to flowcharts and error codes, simplified diagrams that told you which part to swap based on a blinking light. He wasn't used to an engineering schematic that showed the internal fluid dynamics of a governing system. He was looking at the source code of the iron. "Look at the date," I said, pointing to the title block in the bottom right corner. "September 1974. This generator was one of the first VTA28 units configured for standby hospital application. Now look here." I traced a hydraulic line with my finger, stopping at the symbol for the servo proportional valve. "This is the component causing your problem. In the original design, the valve is mounted horizontally, with the pilot drain port facing down." I looked up at the VTA28, looming over us like a judge. "And if you look at your engine, that is exactly how it is installed. It matches the drawing perfectly." "So it's installed correctly," the manager said, crossing his arms, a hint of vindication returning to his voice. "You just proved the previous teams were right. If it matches the blueprint, the installation is correct. The part must be bad." "It matches the original blueprint," I corrected him, keeping my voice flat. "But engineering is not a static process. It is a conversation between the designer and the real world, and sometimes the real world talks back." I reached back into the envelope and pulled out a single, smaller sheet of paper. It wasn't blue, it was pink, a salmon slip. In the world of heavy machinery, pink paper means a correction. It was a technical service bulletin, numbered TSB 78-114, dated 4 years after the generator was built. "This is what we call a silent recall," I explained. "In 1978, the engineers realized that when these valves are mounted with the drain port down, they accumulate microscopic air bubbles in the pilot chamber. Under normal, steady loads, it doesn't matter. The air compresses, the valve moves, and the lights stay on. That is why this machine ran perfectly for 30 years. It was powering incandescent lights and simple motors. It was pushing a dumb load." I stood up, holding the pink slip next to the blueprint, forcing him to see the timeline of the failure. "But you don't have a dumb load anymore. You installed that new MRI wing 6 months ago, didn't you?" The manager blinked, surprised. "Yes, in February. How did you know?" "Because that is when your problem started," I said. "The MRI machines push harmonic distortion back into the line. They make the voltage jagged. The governor tries to chase those jags. It has to oscillate the fuel rack hundreds of times a second to keep the frequency steady. When the valve tries to move that fast, those trapped air bubbles act like a spring. They create a hydraulic lock. The valve pushes, the air bounces back, and the spool starts to flutter. That heat I felt? That scream we heard? That was the valve fighting its own installation." I pointed at the pile of discarded electronics in the corner. "The computer saw the flutter and threw a signal instability code. Your certified technicians saw the code and replaced the sensor. Then they replaced the computer. Then they replaced the wiring. They spent $60,000 chasing a ghost because they were reading the error logs instead of the history books. They were trying to fix a software glitch, but the problem was that a mechanic in 1974 mounted a valve upside down because nobody told him not to. The realization hit the manager like a physical blow. I watched his eyes move from the pink slip to the pile of expensive, useless boxes. He wasn't just seeing a repair bill. He was seeing the architecture of a scam. It wasn't that the previous shops were malicious. They weren't trying to rob him. It was worse than that. They were incompetent. They had charged him premium rates for their inability to look beyond the screen. They had treated the symptom of instability without understanding the pathology of the machine.
"So," he said, his voice quieter now, stripped of its administrative arrogance, "the valve isn't broken?" "No," I said, folding the blueprints carefully and sliding them back into the envelope. "It's just confused. It's trying to do a job it wasn't oriented to do. We don't need a new valve. We don't need a new computer. We just need to drain the system, unbolt the valve, and rotate it 180 degrees so the drain port faces up. We let the air out, and the ghost goes away." I looked at the clock on the wall. "I have 40 minutes left. That is plenty of time to turn a wrench. But I am going to need you to step back. The theoretical part of this lesson is over. Now I have to get dirty." The manager nodded slowly, stepping back behind the yellow safety line. He didn't look at his watch this time. He looked at the machine with a new expression, not as a piece of junk, but as a puzzle that had finally been solved. I picked up my wrench. The easy part was the diagnosis. Now came the hard part, fighting 30 years of rust to prove I was right. The transition from diagnosis to repair is a shift from the intellectual to the physical. It is the moment where you stop being a detective and start being a surgeon. The theory was sound. The blueprints were clear. But none of that mattered if I snapped a 30-year-old mounting stud flush with the engine block. If I broke a bolt now, this 1-hour fix would turn into a 3-day nightmare of drilling, tapping, and cursing. The manager stood behind the safety line, watching me with a mix of hope and anxiety. He didn't understand that the most dangerous part of the job wasn't the electrical load, it was the rust. I started by isolating the hydraulic circuit. I cracked the fitting on the supply line, and a hiss of escaping pressure was followed immediately by a weep of hot oil. It ran down my arm, soaking into the sleeve of my coveralls. It was 160 degrees, hot enough to be uncomfortable, but I didn't pull back. You have to feel the fluid to understand its condition. I rubbed the oil between my thumb and forefinger. It was gritty. That confirmed my suspicion about the internal wear, but it also told me I had to be fast. The system was bleeding out, and I needed to get the valve off before the reservoir drained completely. I selected a socket for the 4 mounting bolts. They were painted over, encased in a thick layer of Cummins beige enamel that had hardened into a ceramic-like shell over 3 decades. I had to tap the socket onto the bolt head with the heel of my hand to break the paint seal. I attached my ratchet, took a breath, and applied pressure. This is where experience counts. A rookie pulls on the wrench. A specialist feels the tension. I applied steady, increasing torque, listening to the steel. I was waiting for one of 2 feelings: the sudden, spongy yield of a bolt about to shear, or the sharp, violent crack of the threadlock breaking free. Crack! The first bolt gave way, then the second. The third fought me, requiring me to brace my boot against the engine skid for leverage, but it eventually surrendered with a screech of dry metal on metal. When the 4th bolt came loose, the heavy steel body of the servo-proportional valve slumped in my hands, slick with oil and history. I pulled it free from the engine block and carried it over to a clean rag I had laid out on the floor. The manager leaned in, trying to see what a $60,000 problem looked like. It looked underwhelming. It was just a block of machined steel with some ports and a solenoid. But I turned it over, exposing the mating surface that had been pressed against the engine since the Ford administration. "Look here," I said, pointing to a small, recessed cavity on the inlet port. Inside the port was a tiny, sintered bronze filter screen. It was no bigger than a thimble, designed to catch microscopic debris before it could enter the delicate spool assembly. It is a feature often left off the main diagrams, a piece of professional malice
that engineers buried deep inside components, knowing that only someone who takes the machine apart will ever find it. The screen was completely blind. It was packed solid with a thick black sludge, a composite of varnish, metal shavings, and the disintegrated remains of rubber seals from the 1980s. "This is your signal error," I told the manager, scraping a glob of the sludge away with my fingernail. The modern shop saw computer code that said the valve wasn't responding fast enough. They thought the electronics were slow. The truth is, the valve was trying to move, but it was suffocating. It was trying to pull hydraulic fluid through a wall of mud. I spent the next 10 minutes in a rhythmic trance of cleaning. I used cans of brake cleaner, blasting the solvent through the screen until the runoff changed from black to clear. I used a brass wire brush to clean the mating surfaces of the engine block, removing the old gasket material with surgical precision. You cannot rush this. If you leave a single ridge of old paint or a speck of grit, the valve won't seat flat. The oil will bypass, and the generator will fail again. I wiped down the steel until it shone, treating the cast iron with the reverence it deserved. Then came the correction. I picked up the heavy valve, but instead of orienting it with the solenoid label facing up, as it had been for 30 years, I flipped it. I rotated the entire assembly 180 degrees. It looked wrong. The label was now upside down. The wiring harness had to be twisted slightly to reach the connector. To a parts changer, this would look like a mistake. But as I pressed the valve against the block, the ports aligned perfectly. The internal geometry of the casting was symmetrical, but the flow path was now inverted. The pilot drain, previously at the bottom where air could be trapped, was now at the top. The air bubbles that had caused the hydraulic lock would now float harmlessly out of the system and return to the tank. I threaded the bolts back in by hand, ensuring they didn't cross-thread. Then I took my torque wrench, not a guess, but a calibrated instrument, and tightened them in a star pattern. Click, 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 click. 45 foot-pounds of torque. That was the difference between a loose seal and a stripped thread. I reconnected the hydraulic lines, feeling the threads bite cleanly. I wiped the excess oil from the block, leaving the machine looking not just repaired, but respected. I stood up, my knees cracking, and looked at the manager. "The obstruction is gone," I said, tossing the dirty rag into the trash. "And the trap is open. Now we see if she breathes." "Clear!" I shouted over the hum of the ventilation fans. I didn't wait for a confirmation. I nodded at the manager, signaling him to initiate the start sequence for the second time. He hesitated for a fraction of a second, his finger hovering over the button. He was remembering the violence of the previous attempt, the smoke, the shaking, the scream of the hydraulic fluid. He was afraid that this time the machine wouldn't just scream, it would explode. But he pressed it. The air start system engaged again with that familiar pneumatic hiss, but what followed was fundamentally different. There was no grinding struggle. There was no detonation. The compression caught on the first rotation, and the VTA28 woke up. It didn't roar in anger. It barked once, a sharp, authoritative report of 12 cylinders firing in unison, and then immediately settled into a rhythm. The lope was gone. That jagged, hunting surge that sounded like a dying beast had been replaced by the steady, heavy percussion of a freight train. Thrum, 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 thrum. It was a sound of absolute mechanical confidence. I watched the vibration isolators on the floor. 10 minutes ago, they had been shivering violently, transmitting a structural panic into the concrete. Now, they were absorbing the normal harmonic frequency of a balanced engine. The dust on the floor stopped rippling. The pile of cardboard boxes in the corner stopped shaking. The room felt calm, anchored by the heavy, rhythmic gravity of the spinning crankshaft. I walked over to the control panel, standing next to the manager. He was staring at the tachometer with his mouth slightly open. The needle on the analog gauge wasn't sweeping back and forth between 1600 and 1900 RPM. It was glued to 1800. It looked like it had been painted onto the glass. "Look at the frequency," I said, pointing to the hertz meter. It read 60.00 hertz. Not 59.8, not 60.2. It was dead center. The governor, now free of the trapped air bubbles and the sludge that had blinded it, was making micro-adjustments faster than the human eye could track. It was locking the engine speed to the grid requirement with a precision that the digital sensors couldn't comprehend. "It's stable," the manager whispered, as if saying it too loud would break the spell. "But we haven't applied the load yet. It always drifts when the hospital load hits it." "It drifted because the valve was fighting a hydraulic lock," I corrected him. "It drifted because the air in the line was acting like a spring, bouncing the fuel rack around. The air is gone. Hit the transfer switch." He looked at me, panic flaring in his eyes again. "If I transfer the load and it fails now, we drop the ICU. The UPS batteries only have 10 minutes of reserve left." "Hit the switch," I said. I didn't raise my voice. I just stated it as a fact. "The machine is ready." He took a deep breath, reached out, and turned the heavy black dial of the automatic transfer switch. Clunk. The sound of the contactors closing was heavy and final. Instantly, 800 kilowatts of electrical demand, the elevators, the chillers, the lights, the operating theaters, and yes, the harmonic-generating MRI machines, slammed onto the generator. This is called a step load. In a weak system, this is the moment the engine bogs down, the lights brown out, and the black smoke pours from the stack as the fuel system panics. The VTA28 didn't even blink. There was a slight change in the pitch of the turbochargers, a deepening of the whistle as they spooled up to shove more air into the cylinders, but the RPM needle didn't move more than the width of a human hair. The lights in the generator room remained perfectly bright. The engine took the weight of the entire hospital on its shoulders and simply leaned into it. It was doing exactly what it had been designed to do in 1974. The manager frantically tapped at his laptop, pulling up the live data from the power quality analyzer. He was looking for the signal instability that had plagued them for months. He was looking for the jagged waves of the harmonic distortion. "I don't understand," he stammered, scrolling through the graphs. "The harmonics from the MRI are still there. I can see the noise on the line. But the generator isn't hunting. The fuel rail pressure is flat. How is this possible without the new computer?" "Because the valve isn't fighting the noise anymore," I said, wiping a smudge of grease from the glass face of the oil pressure gauge. "The valve is dampening it. By flipping the orientation, we allowed the hydraulic system to absorb those micropulses instead of reflecting them back into the governor. You didn't need a faster computer to read the noise. You needed a smarter hydraulic circuit to ignore it." He looked from the screen to the engine, and then finally, at me. The arrogance was gone. The certainty that modern is better had evaporated in the face of physical reality. He looked at the $60,000 of wasted plastic parts in the corner, and then at the single, dirty, 30-year-old iron valve that was currently holding his hospital together. He realized that he had almost thrown away a $1 million asset because he trusted a screen more than a mechanic. "It's fixed," he said. "It's actually fixed." "It was never broken," I said. I walked back to my satchel and started cleaning my tools. I wiped the oil from my torque wrench before placing it back in its case. I coiled the stethoscope. I treated my gear with the same respect I had just shown the engine. The manager watched me pack. He looked like he wanted to say something, an apology perhaps, or a justification, but he couldn't find the words. He was still processing the paradigm shift. He had been convinced he was the victim of a scam by independent mechanics. He was just now realizing that the scam was his own blind faith in the idea that newer technology always solves the problem. I buckled the leather strap of my bag. I picked up the yellow envelope containing the blueprints and the pink TSB slip. I hesitated for a moment, then walked over to the manager's desk and laid them down on top of his clipboard. "Keep these," I said. "The next time a technician tells you this machine is obsolete, make him read the pink slip. It's the user manual for the real world." I didn't wait for a thank you. I didn't wait for him to sign off on the work order. The sound of the engine was the only signature I needed. It was running at a perfect, rhythmic 60 hertz, a heartbeat of iron and oil that would keep the lights on long after I was gone. I walked out of the sterile room, leaving the noise behind, my mind already shifting gears to the next job, the next machine, the next silence that needed to be broken. The purchase order for the Caterpillar C175 was shredded before I reached the parking lot. That is the immediate consequence of competence. It disrupts the flow of capital toward unnecessary consumption. The facility manager, once ready to spend $2 million on a replacement, suddenly found himself the guardian of a perfectly functional asset.
The modern maintenance contractor, the firm with the tablets and the clean uniforms, was terminated for cause. They hadn't tried to cheat the hospital. They truly believed the machine was broken because their screens told them so. That is the tragedy of the modern service industry. It isn't malicious, it is hollow. It is a vacuum of skill filled by the noise of commerce. I sat in the cab of my truck, the dashboard glowing in the dim light of the parking garage, writing out the invoice. It wasn't for $60,000. It was for travel, 2 hours of labor, and a consumables charge for a can of brake cleaner and a rag. The total came to under $2,000. When I handed it to the manager, he looked confused again. He was conditioned to pay for the attempt to fix things, where the cost scales with the complexity of the failure. He didn't understand that he was paying for the 30 years of experience that allowed me to fix it in 17 minutes. I wasn't charging him for turning the wrench. I was charging him for knowing which bolt to turn. He paid it with a shaking hand, realizing the massive gap between the value I provided and the price I asked. This is where the concept of the scam gets interesting. The manager had accused me of running a scam because I worked outside the system. But the real scam was the system itself, the ecosystem of parts changers and diagnostic fees that exists to extract value from ignorance. They had convinced him that an engine built in 1974 was a liability. They had convinced him that iron has an expiration date. But looking back at the hospital, seeing the lights blazing in the operating theaters, powered by a machine that was built when Nixon was president, the truth was obvious. The machine wasn't the liability. The technicians who refused to learn its language were. The VTA28 was no longer a sleeping giant or a dinosaur. It was a sentinel. Down in that basement, vibrating at a perfect 60 hertz, it was doing exactly what it was designed to do: protect human life. It didn't care about the harmonic distortion from the MRI machines anymore. It didn't care about the digital age. It just drank diesel and spit out electricity, indifferent to the changing world above it. It had been restored not just to functionality, but to dignity. The voice of the machine was no longer a scream of sheer. It was a rhythmic chant of reliability. There is a specific, heavy feeling you get when you walk away from a job like that. It isn't pride exactly. It's vindication. We live in a world that tells us everything is disposable. If your phone breaks, get a new one. If your car has a check engine light, trade it in. If a generator hunts at idle, scrap it. We are losing the ability to fix things because we have stopped listening to them. We look for the error code instead of feeling the heat in the hydraulic line. We trust the sensor instead of the bone behind our ear. We are forgetting that the physical world has rules, and those rules don't change just because we invented microchips. The art of diagnostics is dying, replaced by the algorithm of replacement. I started my truck. The rumble of my own diesel engine felt small, almost polite, compared to the beast I had just awakened in the basement. I checked my mirrors. The hospital was just a building again, not a crisis center bleeding money. The $17,000 an hour of downtime had evaporated into the ether. The panic was gone. All that remained was the steady, rhythmic truth of good engineering. I put the truck in gear and rolled out. There was another plant 3 towns over with a turbine that wouldn't start. Another manager convinced his machine was dead. Another set of blueprints waiting to be read. The machines are always talking. There are just fewer of us left to hear them. The heavy steel door of the generator room clicked shut, sealing the noise inside. But the lesson remains loud and clear. If you rely on parts changers to maintain your legacy, you deserve the bill they send you. The machine isn't broken. You just stopped listening. Subscribe to join the few who still know the language of iron.